Good morning, everyone, and welcome once again to another JKMIC Friday seminar. So on behalf of the University of Queensland and the Sustainable Minerals Institute, would first like to acknowledge the traditional owners of the land on which we meet, the Turrbal and Jagera people, and pay our respects to their ancestors and descendants in their continuing connection to country. So it's my great pleasure today to welcome Associate Professor Kirsten Corin. Kirsten is the head of Flotation Chemistry with the Centre for Minerals Research in the Department of Chemical Engineering at the University of Cape Town, where she manages the Reagent Research Group. Her research is focused on the chemistry of flotation with three important areas of interest: water quality within flotation, chemistry of grinding and flotation, and electrochemistry of minerals. Her presentation today is titled Going with the Flow, Appreciating the Role of Water Quality Within Flotation. So please join me in welcoming Kirsten.
Daniel. Great, so thank you very much for having me here today. It's lovely to be in Brisbane and visiting the university. I just thought before I talked about water and flotation, I'd just introduce you to the Centre for Minerals Research. I'm not sure how many of you are familiar with us. I see quite a few past members in the audience, but for those of you who don't know us, we're based at the University of Cape Town, and our research is spanning across all of minerals processing from mill to end of concentrate. I don't know if this is this on? No? Yeah, just have to activate the screen somehow. Okay. Now this should work. There we go. Right, so we have a focus on three main areas. We focus on mineralogy, flotation, and crushing. And we consider ourselves quite lucky that we have all three of those focus areas in the same center. It's quite unique for minerals processing across the world. We do computational research, lab research, and industrial research, as well as a component of modeling. So we say we do about 40% lab research, 40% computational research, and 20% industrial research actually on site at the mines. And we're trying as a research purpose to develop models that will describe the various processes that are happening on minerals processing sites. And by models, we mean the broad scheme of models, not necessarily just numerical models. Our comminution research, you can see here a couple of the instruments. Those are site-based instruments, but our comminution team look at anything from crushers to ball mills, stirred mills, all the way through to modeling circuits. Our flotation research team, similarly here, you can see a number of our pieces of kit, and we focus on anything from the chemistry of the process through to the rheology, novel cell design, and again, modeling circuits. Our process mineralogy team is, we're very fortunate to have that because it integrates our comminution and our flotation. If we know what the mineralogy is, we can really understand what's going to happen between the two processes. And we are very fortunate to have our own QuemScan instrument. So we do our own mineralogy, and we have access to an X-ray computed tomography instrument, which sits out in Stellenbosch, which is really not too far away from Cape Town. We also have a technology transfer arm. We term them MP Tech. These are the people that go to site. They aren't specific people. The whole center is part of MP Tech as needed, depending on what's required on site. We'll send different people. But we go to site, we'll do circuit surveys, we'll do optimizations, we'll check if there's a particular problem that a site is having, and we can go and address the problem if we can. And we also recently are starting to do a lot more training than we previously did. Obviously, COVID has changed the portfolio. Sites are much more difficult to get onto now because of safety concerns. So we've moved to a lot more training than we did in the past. We've also started doing fit for purpose training. So a site can come to us, they want their mates trained in a particular way with particular topics, and we'll design those training courses especially for them. Right, so onto the topic of today. So water within flotation is just one of my research topics, but I thought instead of giving you a huge amount of technical information today, because I know most of you aren't flotation chemists, I'd take a step back and just talk about water quality in general, trying to understand why is it important. So the overarching questions that we ask in this particular research area is how dirty can our process water get before it starts to impact the process? These are the sorts of questions that a site needs to ask if they're going to be recycling water, and I'll talk a little bit about that later. We also need to understand which components are problematic, because if it's only one particular component or two components in the process that are problematic, can we treat them, get rid of them, and then not worry about the rest and let the rest just do what they do? And then, of course, we need to know what measurements we need to make. Measurements at the moment are only done on site for environmental purposes, not for chemistry purposes. So it's important for us to understand which measurements should be done on site, which ones are not currently being done, and implement them as such. But yes, so let's take a step back. What exactly is water quality when we talk about water quality? And this is not within the bounds of minerals processing, but just in general. So of course, water quality depends on a number of things. It depends where you are in the world, and it depends on how you're using your water. You know, is it sewage water? Is it a river? Is it a lake? Is it the sea? And we measure our water quality by a number of different standards, most of them chemical. So we would send a water sample away to a certified lab, and you'd get a composition of what's in your water. They'd also measure, you know, standard things like pH, EH, temperature. We also look at the biological components. For example, you want to know if the water is healthy for you to drink. You know, does it have microbials or bacteria that can be harmful to you as human beings who have to drink the water? And there's a number of other ways that we test these waters, but water quality testing labs will be ISO approved to test and make sure that it's drinking water level or it's not. And if it's not drinking water level, of course, you can use it for other purposes, or you can clean it and purify it to make it drinking more potable level. Water quality depends on how we use it. So water might be pristine in your river or your lake near your home, but if somebody upstream from you is an industry and they're dirtying the water, you're not going to know that. I mean, water is going to look the same regardless of what's in it, right? Water's clear. We don't know. You can't look at water and say it's safe to drink. So it really depends on what we've done to that water and where you are based as to what your water quality is going to look like. Are you based in an industrial area, an agricultural area, or is it just recreational water, or is it just a regular, you know, lake or river where you know that it's relatively safe to use that water? These are some of the measurements. I'm not going to read the whole slide, but these are some of the measurements that we traditionally make on water quality. The understanding water quality has always been, as I said, for environmental reasons, and in most cases only for potable reasons. So you want to be able to drink the water. So these are the sorts of measurements we would make at the various labs. Particularly the bacteria and viruses have become more and more prevalent now that we can test for COVID in various water supplies. This is being done more and more often. But generally, there's a standard number of tests that get done, and you get an answer, is your water potable or not? They don't necessarily give you all of those tests, though. So sometimes, depending on which lab you go to, you might not get all the information you need as an engineer who wants to use that water for different purposes. Why is it important? Why do we need to know what those measurements are? Well, the pH of the water really has a huge impact. Fish and plants, algae, and various biological species can only survive in certain pH waters. Humans can only drink a water of a certain pH. The pH can vary. I mean, some of the bands are quite large. You can see there that humans can drink water and be safe anywhere from pH 4 up to pH 10. You can often taste the difference between those waters. You can taste, a mineral water that you buy in a bottle that's up at a pH 10. They claim that it's healthier for you. You can taste the difference between that and a pH 4 water. Even included in this slide is your human blood that sits at a pH of 7. And if your blood goes out, if your pH is out, you can get really, really sick. So pH is one of the really important ones, and it's so simple to do. There are so many probes. You can just stick them in your cell and you can get a pH reading anywhere in any kind of slurry. It's so easy. Dissolved oxygen, also a really important one, often overlooked. Dissolved oxygen is just something that happens because oxygen just dissolves into the water over time in a natural environment, depending on how much air it's exposed to. It makes a huge difference to plant life, to animal life, and to humans as well. And you can see there that, if you at really low dissolved oxygen levels, you can kill off your plants and your animals that are living in your water. So we really need to know these sorts of parameters. Temperature and dissolved oxygen are related to one another. Obviously, as your temperature rises, you've got slightly less pressure, so your oxygen can escape out the water. So we need to know temperature as well. What's interesting, though, is if you were to take a water sample, for example, from a site or from a river or from a lake and bring it back to a lab for testing, obviously in that travel time, the temperature changes between when you took the sample and when you actually measure that temperature. So even that travel is important when you're doing your testing. Test it there and then in that river. You've got to know what that temperature is right there and then to understand the health of the system. Conductivity is important. Conductivity refers to dissolved salts or dissolved ions in the system. Your conductivity is an overall level of the number of ions that are there. It can be related back to a measure such as ionic strength, but it can't tell you which ions are there. So it just tells you the overall charge of the electrical charge of the system. But conductivity is also important. Only certain levels of conductivity are going to be suitable for life to use or for potable water to sustain plants and animals. Redox potential, we all know redox potential, we all did it in undergrad, but even redox potential, you have to understand what levels of redox potential are suitable for people to use. So you can see there on the right-hand side, you've got that lovely little graphic there where it shows you at what levels your redox potential is. So there's quite a range of redox potentials that are suitable for people to drink. You know, there's tea there, there's soda, various redox potentials are okay, but some of them are not going to be okay and it's going to destroy your system. And particularly when we get to minerals processing systems, your redox potential becomes really important because of the mineralogy of the system. Turbidity can be related to total dissolved solids. It's the amount of particulates in your system, your suspended solids or your precipitates that are there. What turbidity does in a natural system is it actually blocks sunlight. So if your turbidity is too high, your fish are going to die. They're not going to get natural sunlight. It's also going to block access to oxygen if you don't have the sunlight coming in there. So there again, you can see the various levels that are suitable for, in this case, for fish that can, if your fish in your fish tank have the wrong turbidity, they're going to die. You're not necessarily going to be able to, see that it's happening. If you see the water goes cloudy, you don't know why it's going cloudy. So this is another one of these parameters that need to be tested. Organic contaminants are slightly more complex. They're not as easy to measure, and they come from a variety of sources. So in terms of organics, we're looking at herbicides, pesticides for the agricultural industry, pharmaceutical compounds. What a lot of people don't realize is that we humans use pharmaceuticals. We use our, when we have a headache, we take a pill. But when you urinate, that goes straight back into the water supply. And some of those pharmaceutical compounds are not necessarily cleaned because they're not looked for. Nobody's testing for that particular compound in the water. They're not necessarily cleaned out unless they can be filtered or microfiltered out. Some of them are still sitting there. Industrial compounds, of course, coming from local industry, depending on where you're based. But in particular for minerals processing, for the minerals processing industry, surfactants become really important. So, of course, collectors, depressants, frothers, all of them are surface active components or surface active compounds. So if you have particular surfactants in your system, just think about having a shower and letting the soap go down the drain. That's a surfactant. That could influence some process that happens later in the stream if that water is not cleaned. Right, so the sorts of things that are relevant to the minerals processing operations or the industrial compounds that might come from the surrounding industries that are sitting nearby you, depending on what your surrounding industries are. Often minerals processing industries are not necessarily sitting in the same, or not all minerals processing industries are sitting together. Maybe you have a beer brewing company upstream from you, or you have a pharmaceutical company upstream from you, and they don't necessarily clean their water. They don't think those components are harmful, but they might come into the minerals processing stream and act as surfactants, change your mineral surface properties. You're not going to know that unless you understand the water quality. There's obviously water treatment byproducts, particularly in South Africa, which I'll show you later. Quite a number of our mines are using semi-treated sewage water as their primary water coming into the site. And then you've got all sorts of biological and microbiological components sitting in there. And if you don't test for them, you don't know they're there. And all of a sudden something goes wrong on your site and you don't know if you're not testing for it. And then of course, surfactants, which I've already mentioned. And in minerals processing, one of the other things which I'll show you just now is if you're going to recycle your water, all your residual reagents that could still be in the process can come back to the beginning and change the way that your process runs. So just a little graphic here to show you how do we get these inorganic components into the water? Why is there calcium and magnesium in our standard tap water? What's it doing there? Well, it's been leached out of the actual mineral phases. So in a natural river or a stream or a lake, you know, you've got rocks and you've got sand as the bed of your river or lake, that those ions are being leached out of those particular minerals as they come down the mountain, as they go into the river, into the lake. And then they can obviously dissolve into solution. And that's where we get these natural salts from. This is just a table to show you, you know, some of the most common gangue minerals, particularly in South African ores, where you can see on the right-hand side, you can see that composition. You see magnesiums, calciums, sodiums, ions, and those are all the sorts of ions that we see in processed water. And this is obviously where they've come from. They've come from being dissolved out of your gangue mineralogy. Right. So within the South African context, and our context is quite similar to the Australian context, we in South Africa, the mining industry only uses about 3% of our water supply. It's not a huge amount of water by any means, but historically the mining industry is known that to give toxic hazardous discharge out to the environment. Once they finish the process, they send the water out, and historically water wasn't considered a problem, so it wasn't cleaned. Oh, the natural environment will clean it, the plants later down the stream will clean it. It wasn't really a consideration. And if you're sitting in an area where you don't have a huge human population, you worry even less about what your water is going to look like. So it's that historical reputation for really hazardous toxic water that the mining industry struggles with. It's not that it uses a huge amount of water. Interesting on this slide shows you those colorful blocks are where most of our mines are located. So these are where our ore reserves are sitting, our mineral deposits. And you can see they're concentrated mostly up there in the north in the Gauteng and Mpumalanga province. That's our Bushveld igneous complex that I'm sure most of you are familiar with, where we get most of our platinum group minerals. Similarly, here is the water catchment areas of South Africa. Most of the water obviously coming down from the large mountain ranges down towards the sea. If you overlap those two maps, you can see quite a problem. Our water courses don't run anywhere near our mines. So this has always been a problem for the South African mining industry, that you have to bring water to you. And that's costly, you know, so which is why a lot of them are using semi-treated sewage water, or a lot of them are actually recycling their processed water on site to save themselves that hassle of having to bring water to them. Further to this, other than just being in a water scarce area, there's a number of motivating factors that want to make the mine sites use their water more efficiently. And I mean, not least of which is legal compliance. So there's political pressure to make sure that water is used properly so that there is enough water for the human population to use it. Otherwise, mines face closure. They can be charged huge fines for using water inappropriately, especially if they discharge hazardous water. So all of this sparks this need for research into what does water look like on a mine site and how can we use it more appropriately. And what this has all come down to is this concept of what we call the closed water concentrator. So here's a diagram of the closed water concentrator. Lovely simplified diagram. Basically, you know, at the top of the slide there, you get your fresh water in, you mix it with your stockpile, you have a little black box of processing plant where something magical happens. And then you take your concentrates, your tails, you dewater them, you send your dewatered solids off either for further processing in the case of a concentrate, or to a tailings dam or tailings dump for the tailings sample. But that dewatered water that you're left, I mean, the water that's remaining after you've taken the solids out is now this iron-rich process stream. And what do you do with it? Can you, in the first instance, their option one, send it straight back to the beginning of the process? Possibly, depending on the quality of that water. But are we taking the right measurements to know that we can do that? Not yet. The second option there is some sort of treatment and recycle. This could be full treatment. You could treat the entire stream down to potable level, reverse osmosis. Very costly, but you can do it. Or as I was mentioning earlier, it could be partial treatment. You could discover in the research that there's a particular ion or particular bacteria that's causing the problem and treat just that one component of the stream and then send the rest back to the beginning of the processing plant. Of course, there's option 3, which is the traditional way, just reject it, send it out to somewhere else. But now, because of legal requirements, the rejection stream is very costly. You have to treat that to potable level. You have no choice. So that becomes very costly. That's all sorts of other water treatment processes, which are not part of our research, but I know are very costly if you have to go that way. So let's look at within flotation. Water quality within flotation, there's a lot of things to consider. I mean, 80 to 85% of your pulp is water. So you've only really got a small amount of minerals there and the rest is water. And what's in that water is going to impact the surfaces of all of your valuable minerals, the surfaces of all of your non-valuable minerals, the surface of your bubble. And of course, you've got these biological species, which, I mean, let's be honest, the research is quite skim. Nobody knows what they do. And there's so many of them. The variety of microbes and bacteria, you don't know from one day to the next which microbe is going to be on your site. So even that is very, very complex. But you can see there that for each of the various components in your system, something's happening at the surface of each of those components. You've got adsorption of reagents, you've got desorption of reagents, you've got redox reactions happening, you've got all sorts of things happening, dissolution of your mineral phase into solution. And all of those reactions impact that center red block there, that the components that we can actually measure. They're going to impact your pH, your redox potential, they're going to impact the ionic strength of your system, et cetera, et cetera. And so all of these things, unfortunately, all interact with one another. It's not as simple as saying, well, this is that one thing that causes this to happen. You can't narrow it down to just a single process. So it's a very complicated system, and this is where most of our research is focused at the moment. I just thought I'd also give you a brief overview of the sorts of measurements that can be made. So that top line there is the types of measurements that are actually quite often made on quite a number of sites. Not every day, maybe once a month, maybe once a week if you're a proactive site. But you can, with a series of probes, stick them into your slurry and actually measure pH, EH, temperature, dissolved oxygen, all at the same time straight away. It's relatively simple. I know UQ's got a team that are developing these sorts of probes that you can just test all these things straight away. It's not that common though. Most of those measurements, if they're done, a week later, the sample's taken now, sent to a lab, and the lab sends you the results a week later, you're lucky if you get it a week later. It says they're immediate because it can be done. It's not being done. Microbial testing has to be done within 24 hours. Your microbes are going to have changed significantly after the 24-hour window. Ideally, you'd want to be measuring them in situ, but the techniques to measure microbes in situ are just not as robust as they need to be doing it for a minerals processing site. It's just not possible at the moment. Within 48 hours, you can do the salts, right? So all of the ions, they shouldn't have changed too much unless you've had a significant amount of precipitation. 48 hours is okay. But if your temperature has changed significantly or your EH has changed significantly from the time you took the sample to when you're now measuring those ions, then something's changed. So then your ions may not be what you thought they were. There's probably some sort of precipitation going on there. In general, though, what we refer to in our work, which is the generic ionic strength of the system, it's one of the simpler ways of giving an overall idea of how many ions, what sort of level they're at. We have recently, well, not recently, but we have also done quite a lot of work on single ions rather than looking at a generic ionic strength, because we have started to realize that it's particular ions that are having more of an impact than others, and looking at generic ionic strength isn't suitable. But for a mine site, it might be one of those parameters that you could put into a model and it could be put into a process control system, and it would make it simpler to manage. So at UCT, we developed a synthetic plant water recipe. So back in 2005, there was a survey done of a number of the operations up in the Bushveld Igneous Complex, platinum operations. We tested all their waters, and we came up with the sort of average water quality at the time. So you can see there the calcium, magnesium, sodium, all of those ions obviously leached out of your gangue minerals. Okay, you've got a bit of sulfate there that's coming from your sulfides. Nitrates usually coming from explosives in the pit. We haven't seen nitrates increase too much lately, but yes, and then obviously carbonates from standard water. But so we developed this synthetic plant water. We termed it SPW, and it was based on the nature of the gangue minerals in the Bushveld complex. But that was back in 2005. We've done not another huge survey, but we have interacted with a number of sites since then. And we're actually not sitting at this level anymore. The sites are sitting at about 3 times this level, interestingly, across most of the ions. So there hasn't been a particular ion that's increased over and above the others, obviously, because your gangue's going to, dissolve at the same rate. But we're now sitting at about 3 times this recipe. So a lot of our work, we started at 1 SPW, but we've now moved ourselves up. So again, instead of giving you a huge amount of technical information, I've separated the presentation into just different factors that affect flotation. And the first one, I'm going to talk about foams, froths, and bubbles. Of course, foams, 2-phase, only air and water. Froths have the mineral particles in there. So this was some of the very early work we did, 2-phase foam behavior. We've got no minerals present, but we wanted to see whether, because we know the ions are surface active at the surface of a bubble. So we know, that affects that foamy sort of stuff you get at the beach when you've got a bad day, you get that sort of yellowish foam that comes onto the beach. That's your salts and your biological components. They're all coming into the water and causing this foam. So initially, we looked at water recovery. It's a standard measurement we make in the Center for Minerals Research when we do flotation. We don't just measure solids recovery or valuable mineral recovery, but we actually monitor the water as well. So we know how much water is sitting in our froth phase. So you can see there, we went from 1 SPW right the way up to 10 in this case. And you can see your water recovery increases quite significantly as you increase your ionic strength. So stabilizing the bubbles, and allowing more water to be captured between those bubbles, so your water recovery goes up. Similarly, on the right-hand side, you can see there, that's bubble size. As you increase your ionic strength, you decrease your bubble size, which also makes sense, because as you increase the ionic strength of your water, you're increasing your viscosity, you're stopping the bubbles from coalescing, and you're allowing the bubbles to stay more stable. Even as they rise to the top of your flotation cell, they're still going to not coalesce as often as they would when there's less ions present. So those were, and then what we have here is foam stability studies. So what we did is we just used a column. We allow the foam to develop, and then we turn the air on, the foam grows. We measure maximum foam height. How high does it reach in the column? Then we turn the air off and we measure the foam collapse time. So you can see here this correlates quite well with our water recoveries and our bubble sizes. As you increase your ionic strength, your foam grows much taller because your bubbles are more stable, but also because there's more water in there, so the volume is greater. When we turn the air off, it takes a lot longer for that foam then to collapse, which also makes sense, because if your bubbles are more stable, they're not going to coalesce as easily, so they're just not going to burst as easily. Right, so that was the 2-phase work. Then we looked at, very briefly, some recovery and grades. We've obviously done a lot more work than this, but I just wanted to keep it as simple as possible for today. So what we did here was, instead of showing you each individual valuable mineral, we've grouped them all together and we've called them sulfide recovery. So that includes your chalcopyrite, your pyrite, peritite, pentlandite, all included in one measurement. In the platinum industry, it's important for us to consider peritite as a valuable mineral because some of our platinum group minerals are associated with peritite. So in other industries, I know it's a gangue, but for us, it's a value. So we've included it there in the measurements. So you can see there, what this study did was we went from 1 SPW up to 10 again, like we did before. In this case, we've used a depressant as well. So we've increased our depressant dosages 0, 100, and 500. What this does is allows us to measure entrainment. So we can separate true flotation from entrainment. At 500 grams per ton, depressant's a huge amount of depressant. It stops any naturally floatable gangue from floating. So everything you recover that is gangue is considered to be entrainment. So that's why we've got such a high depressant dosage there. But overall, what you can see here is the sulfide recovery in those gray bars, the sulfide grade in the yellow bars. Your recovery is not really impacted all that much by changes in ionic strength. It's also not really impacted very much by changes in your depressant dosage. So on average, your recovery stays the same, thank goodness. But we have seen this. This is quite common for PGM ores. They're very low grade, so our recoveries are quite stable. In terms of grade, though, you see a huge impact. So obviously, as you increase your depressant dosage, you expect to see that big impact. You're trying to get rid of your gang. So that, I think there are some errors. So that increase there, that's expected. You do want that. That isn't something we weren't expecting to see. But what is interesting is this trend here. As you increase your ionic strength across all of your different depressant dosages, you see that decrease in grade. That we didn't expect to see. We thought that as you increase your ionic strength, you're stabilizing your bubbles, you're giving them more space to hold valuable minerals. So, I mean, to hold your gang particles. So your grade should go down. Sorry, this we did expect to see. That's the next section that we didn't expect to see. So your grade will go down. You've got more gang mineralogy sitting there in those bubble surfaces, and that's gonna impact the grade of your valuable minerals. All right, so now in terms of the gang. So using this high depressant dosage method that we've got at UCT, you can see there that on the left-hand side is our floating gang versus water recovery, going from 0 grams per ton at the top, 100 grams per ton in the middle, 500 grams per ton in the bottom. And you can see there that you really are kicking out all of your floating gang. Those lines at the bottom are really, there's such a small amount of gang left behind there that it's really negligible. Interesting, though, what you also can see is that there's less gang recovered for each of your increased ionic strength. So on this left-hand graph, we've got 2 plant and 3 plant. So it's not a huge change in ionic strength, but you can still see that for each set of lines, your 3 plant is sitting below your 2 plant. So we're recovering less gang. That doesn't make any sense, right? Because just now we saw that your grade has gone down, so you should be recovering more gang. Okay, so we looked at entrainment. And there on the right-hand side, you can see those are our entrainment curves. So what we do is we do the calculation, work out how much entrainment there is. The straight line tells us it's definitely entrainment because there's a definite relationship between the amount of gang you recover and the amount of water you recover, directly proportional to one another. We take the slope of that line, and that tells us the entrainment factor. And then we can work backwards across the depressant dosages and get ourselves the amount of entrained gang. What's interesting here is you can see that the lines actually follow a trend in that direction. You're seeing from tap water to plant to 2 plant to 3 plant, you're actually decreasing your entrainment factor. Well, that also doesn't make any sense. We're decreasing our entrainment factor, but our grades went down. So why are we getting less gang in this case? Then why are our grades going down? That doesn't make any sense. Well, actually it does. It seems completely counterintuitive, but it's not. What's happening is when you increase your ionic strength, you're actually stabilizing that bubble to such an extent that you're also recovering so much more water. So you're recovering less gang per unit water, as this graph is showing you. So water is the x-axis in this case. So per unit water, you're recovering less gang. But when you increase the ionic strength, you're recovering so much more water that it overrides the fact that you're actually getting less entrainment. So you end up decreasing your grade. Here's another one to just prove the point to you. So here we've got, again, this is now solids separated out into sulfides, floating gang, and entrained gang. The yellow bars at the bottom there is your sulfides. And you can see there really there's not much of a change in your valuable mineral recovery. The gray bars, your floating gang, you can see, again, not much of a change in recovery of your floating gang. If you look at each depressant dosage, you can see differences. Of course, you expect that. You're kicking out your floating gang. But if you take one particular depressant dosage like we've done there, 0, you can see there's not really a change. There's the depressant in action. As you increase your depressant dosage, you're kicking out all of your gang. And so you expect that downward trend. But this trend is what's interesting here. So as you increase your ionic strength, you are recovering a huge amount more entrained gang. But we just saw entrainment go down. But that was our entrainment factor, entrainment per unit water. So because we're recovering so much more water at the higher ionic strengths, we end up recovering more entrained gangue, even though the amount of gangue per unit water is less. It all seems a bit confusing, but it's true. Again, for this study, we looked at the froth collapse time. And here again, you can see it correlates exactly with what I showed you earlier. Your froth collapse time goes up, takes longer for the froth to collapse when your ionic strength is higher. You can also see a trend there in depressants. As you increase your depressant dosage, your froth collapse time goes down. This makes sense because your floating gangue stabilizes your froth phase. Without it in there, it's not going to take as long to drop. So just very briefly, we've done quite a lot more work than this. As you can see here, there's some terms that I didn't even mention, such as bubble particle attachment and particle settling. But we've got quite a huge suite of results in this particular area. And I just wanted to give you just an indication of some of the responses we've seen. We've seen these huge increases. As you increase your ionic strength, you increase your water recovery, you increase your solids recovery, and you increase that froth stability. But you decrease your bubble size. So even though your froth is more stable, your bubbles are much smaller. We've seen a decrease in xanthate adsorption. This could be a competition between the ions and the xanthate at the surface of the mineral. It could be a competition for the xanthate and the bubble surface when the mineral particles attach to the bubble. It could be a number of different things. We haven't really seen a difference in recovery, although this is PGM ore, and I imagine that if we went to base metals or a different type of ore, we would see changes in recovery. With a higher feed grade, you'd have a much greater response. We did see that change in grade, which is really important. The PGM operations, many of them are grade driven and not necessarily recovery driven. So grade is really important. And if they're going to start recycling their water, they're going to have to take that into account. It may be possible that we can improve that with reagents or improve it some other way, but yeah, and then we saw a decrease in particle settling, which is also really important because if you're going to recycle your water, it's going to become more and more difficult to dewater your process at the end to then re-recover that water to bring it back. And we are seeing that decrease in particle settling time, which is a good thing. Right, so what? Cyril's always taught me you have to have a so what, otherwise what's the point of your presentation? But really it goes back to what I said right at the beginning. How dirty can our water be? How dirty can you allow it to be before your process is going to be impacted? And at what point are you going to have to start implementing treatment options? Or can you just recycle to the end of days and it's never going to impact your process? Maybe if your mineralogy is such, maybe it's possible you can just recycle forever, but I don't think so. I think there's going to come a point where a lot of the mines are suddenly going to wake up and say, oh no, what have I done? Because everything has changed. We've got to understand the mineralogy. We've got to understand the reagents. And maybe by understanding both of those in combination with water, we'll be better able to design the interventions that are going to be needed. What's important for us in our work is this tailoring of the system. So, for example, let's take a system where you're doing sequential flotation. You know, you're floating your copper followed by your nickel. If you take your water at the end of your nickel circuit from the tailings of that nickel circuit and you recycle it back to your copper, all of your chemistry is out. Your chemistry has been designed specially for nickel flotation. Now you're sending it to copper. Might cost you a huge amount in reagents to bring that chemistry back to where you need it for copper. So why do that? Why not take the water at the end of the copper float? Before you even send it to the nickel float, dewater as much as you can out of that, and then change your chemistry again for the nickel float and recirculate within each particular operation as you need it. Similarly, should you wait till the end of your process, maybe at the tailings dam, and then recycle back to the mill? Or should you be considering bringing them back to the beginning of the flotation circuits? All of these sorts of things we call fit for purpose water, trying to understand where do we use the water and how do we use it for best benefit of the process. But yes, so that is my presentation. I hope I have sparked your interest in water and at least understood that it's more important than we've all been led to believe all these years. And thank you so much for having me.
Thanks, Kirsten. We'll open the floor up to any questions now, Lisa.
Of course.
Of course. Thank you, Kirsten. That was such a fantastic talk. I'm really glad that you brought it back to the basics to give the overall value of it. I'm going to go jump back into the details. So the work that you're doing, and I think it's very nicely showing that when it comes to impact of water chemistry on bubbles, you've got the surfactants that change the surface tension, and then you've got the salts that change the water structure, changing the thickness of the layers. But there is a third potential component where you do have some interface destroying chemistries as well. And one of them that's been flagged is things like sodium silicate. So where do you see your work going in that direction?
That's a very interesting question. We haven't looked at sodium silicate, but we have done other work in the center looking at sodium silicate as a potential dispersant and a potential depressant. And that has definitely shown promise, whether it's promise because it's disrupting the water between the bubbles.
I think that's a harmful side effect, if anything.
Yeah.
So that's great. Thank you. Another thing that I actually think that we should do together, should be our next joint paper, is you've got an established method for looking at entrainment. Yeah. So we here at the JK, when we look at entrainment, we use a modeling method that's been developed through P9. Yeah. I think we should do a side-by-side assessment.
We should, absolutely.
Yeah.
That would be lovely.
Let's do it.
Thanks, Kirsten. So just a question, is it sufficiently sensitive and important that you should do baseline on your water for your flotation experiments, etc., at the start in order to benchmark that and compare it with results from other, sources experience at times? Is it that sensitive that we should be doing that and it should be a part of every experiment?
Yes, absolutely. I would support that fully. What your benchmark is depends on how you place it. I know a lot of labs across the world are using tap water as a benchmark. Our benchmark is 1 SPW because we've been using that SPW recipe since 2005. So all of our previous work is based on that recipe. So we can always benchmark back to that. But I know a lot of labs are using tap water as their benchmark. Although tap water in Brisbane and tap water in Cape Town are two different waters, but still, if you know the chemistry of that tap water, it should be good enough as a benchmark. But yes, you have to have a comparator, and it is sensitive enough to see the differences, for sure.
Yeah, please don't drink it. Hi, Kirsten. Thank you for a great presentation. We all understand that the water does influence how our minerals are going to behave in the flotation circuit, and that is something that is not talked about enough. I absolutely agree. So most of the work you've shown, you're basically using that recipe, which what I understood is based on ions concentration in the water.
Yes.
How about residual reagents? Have you done any work on that? And if so, how do you see testing for the concentration of those reagents? Because, they have variable chemistry and it's really hard to know.
Yeah, so we have done work on residual reagents. We definitely see a difference as you change the composition of the water, depending on how you change the composition of the water. But overall, in general, you're getting less reagent absorbed onto the mineral surface when you've got the higher ionic strengths in general, not always. But the way we measure residual reagents obviously depends on the reagents, but we use UV in most cases. Xanthate, it doesn't matter which xanthate it is, xanthate absorbs on the UV spectrum at a particular nanometers, and it always absorbs there. We also have a method, the Dubois method, for doing depressants, also by UV. So you have to color them before you can use the UV. We haven't got a method yet for frother, but we are testing out a frothing column method to be able to test frothers, because it would be so much simpler than putting it through an analytical instrument. Do you have a set frothing column height and diameter, and you just put your water in there and see how it foams, and you go, okay, well, that's my residual frother then, because my froth height reached that level. That's what we're testing out at the moment. We're not quite there yet, but yeah.
something I've been mulling over in terms of looking at residual frothers is to just do a water recovery test in the absence of solids.
Yeah, well, it's the same as doing a froth column study. As I say, it depends which one you find more accurate, I suppose.
Well, just most labs have a Denver cell in the lab, not a column. So
yeah, okay, I suppose.
Yeah.
We've got a million columns. There was a question at the back.
Yeah. We've got an online question from Tanya. Are we able to unmute her? Okay. Okay, Tanya, I've unmuted you, so you should be able to ask your question now.
Can you hear me there?
Yes.
Yeah, sorry. Look, my question was just around, I guess, when you're actually working, I guess, from the engineering side and your site hasn't been built yet to maybe take all the measurements that you want from your water samples, and you may only have, I guess, limited test work. What would be your approach in terms of thinking about water quality, how that could recycle on your site that I guess hasn't actually been built yet? What analysis would you do maybe in your flotation test work to try and figure that out, or is there not really a hard and fast method to do that?
No, that's a great question. Thank you, Tanya. Yes, we have what we call a dissolution protocol. So if you know the mineralogy, or you can get some sort of drill core sample, you can stick it into a grinding mill and test how much of the sample dissolves over time. So you can get an idea of what your water might look like over a certain period of time, or at least which ions are going to be prevalent. And then you can take that same sample from your grinding mill, obviously, into a float cell and see how it's going to float. But it's a repetitive thing you have to do over a certain amount of time. But you can do it on greenfield sites that haven't been built yet. Absolutely.
Yeah, okay. And then in terms of getting that type of work done, is that a standard kind of thing that people do, or is there only specific places that do that type of work?
No, it's not a standard thing people do at all. It was developed quite recently by one of our research team members on our Horizon 2020 project. And yeah, you need, well, I mean, you just need the specialized expertise, but anybody could do it for you if they have a grinding mill and access to an assay lab.
Yeah, okay, fair enough. Thank you.
Yeah.
Take one more question from online. So we have a question from Roberto. Is the saturation indices in water can be used to characterize the water quality for mineral processing like flotation washing plants? Because the mineral water interaction may have the possibility for secondary minerals to precipitate.
Yes, absolutely. That is something we are still exploring. We haven't done it yet. But yes, of course, each ion type will have a saturation level at which it can reach before it starts to look for other ions to precipitate. That is something we are going to have to start doing, and we're probably going to have to do it by modeling, be the simplest way to do it. But definitely that is a possibility to do that kind of work.
Hi, Kirsten. Just a question out of curiosity. In passing, you mentioned that between your first extensive surveys of the plant water in the Bushveld complex and later surveys that it's increased from 1 SPW to 3 SPW. Has anyone looked at why that is?
It's the dissolution of the minerals over time. A lot of the Bushveld complex sites are recycling their water already. Some of them, fortunately for them, some of them have tailings dams where they're able to pull the water from the bottom of the tailings dam. So over time, there's actually almost a cleaning effect on that water. So the water is not coming out as dirty as it would if you recycled it straight away. So that's the progression has been a bit slow, but some of the sites are already recycling. So we can see that progression happening. Some of them are actually higher than 3. The average is about our 3 SPW level. Yeah, but it has, I mean, that was 2005. We're in 2023. So, we're looking at 18 years. It's going to take a long time for them to get to 10s if they ever get there. There will be, as the question before, there will be a solubility limit where the sites just, even if they're recycling, maybe there's going to be precipitation. You're going to have to clean that water first or filter out whatever's there before you recycle again. But yeah, though I don't know that they're ever going to reach the 10 levels. But comparatively, I mean, there's sites that are floating in seawater, and those are sitting at what would equivalently be 25 plant water for us. So if they can use 25 plant water, you know, why can't the other sites? It just becomes very corrosive to your instrumentation. Yeah, and a different ion suite, of course.
Hi, Kirsten, great talk. My question is around what's your take on this? Like when you were doing that study, you showed that gang recovery was increasing, right, for sulfur. And did you ever happen to test it by changing the pH as well? Because I think it really changes your water chemistry. And so basically it changes your zeta potential and all that if you go to the fundamentals of it.
Yeah, we've looked at zeta potential over a range of pHs. It does definitely change. The thing about PGM ores is because of the huge gang content, they self-buffer back to about a pH of 8 or 9 regularly. So to change pH in your system isn't something that would make sense to the industry, but it is something we've looked at on a fundamental level. We've definitely used zeta potential on pure minerals to test, and there is definitely a change. As you change pH, there's definitely a change in the surface charges of your minerals. Absolutely.
Right. And just another quick one. So maybe you were saying that you were not seeing a sort of significant change when you were changing the concentration, or I saw that somewhere in your slides. Was that maybe because you have like very rich sodium and calcium ions that are highly positive, and then on the counter side, you have sulfate ions that basically precipitate on your mineral surface, and then they cancel each other out? And
you mean a change in recovery, or are you talking about a change
recovery.
in water?
So your reagent was not maybe affecting well because now you have counter ions basically relative to the positive ones.
It's quite possible. We haven't seen precipitation at the mineral surface yet, so that we're not seeing at the present ionic strength levels that we've been using. But it is quite possible that at some point they will start to precipitate. I think we did tests. I think it was about 15 times our plant water recipe, and we got precipitation straight away while you're busy making the water. And that, so there will be precipitation, but whether it's happening within the time frame that we do our tests, I don't think so, but it could happen on site in the much longer residence times, yes. Yeah. There's definitely sites in South Africa that precipitate out the gypsum, and that's how they clean their water. They don't actually use a water purification process at all. They just precipitate out the gypsum and then use the water again. So removing the calcium sulfate's relatively simple. And then they use the gypsum to build houses, which is wonderful.
I have a question of my own. So you mentioned the ionic strength was sort of like an average of everything, and then you found some specific ones had an effect. What were some of those specific ions?
Yeah, so they're the usual suspects. You know, the divalent ions have a bigger impact than the monovalent ions. But in general, I mean, if you just have to go through the old literature to see the calciums, the sulfates, thiosalts, those sorts of things have a bigger impact. But it is all mineral dependent. So it really depends on which valuable mineral you're looking at or which gang minerals in your system. Different ions are going to have different impacts. So it's not a one size fits all, not one answer is going to answer your question, but in general, it's usually the calcium sulfate. We've seen magnesium have a huge impact on one of our ores. But yeah, monovalent versus divalent, definitely. We haven't looked at trivalent only because we don't find it on site. So if on another site you might have aluminium sitting in your waters, then trivalent would make sense. But for us, trivalent's not currently there, so we don't use it. Iron's 3, but iron is not, interestingly, in our waters. Iron is sitting on the surface of the minerals, precipitating out, guaranteed. Yeah, iron's not sitting in the water quality suite, which is interesting. Yeah. Iron is in the water, though. It's there, but by the time you are measuring the water quality, you can't see it anymore. That's right.
Hi, Kirsten. My name is Wanda. Yeah, so great talk today. And they say that water is more important than diamonds. So this is great research that you're doing. I just had a quick question about the xanthate adsorption. you showed that it decreases when your ion strength is increasing. Is there any link with electrochemistry from that difference, like ion strength increasing, that adsorption decreasing? An explanation around electrochemistry?
I'm surprised you asked that question. You should know that. Yes, we have seen. We have seen the changes in electrochemistry. So we do see smaller differences in the rest potential profiles. When you've got the higher ionic strengths, there's more ions in the system, so there's less variation. We have also seen we recently did some impedance studies, electrical impedance, and we definitely saw changes in the response to the collector when you've got the ions present. We haven't. Yeah, the student has analyzed all the data. I still have to get my head around her data because EIS is very new to us, but there's definitely changes. Yes, I can't say which way they go, but in terms of adsorption, yes, we definitely see a decrease in the adsorption of the xanthate. So definitely more residual xanthate in the system when the ions are present, which also could be a cost saving effect. If you've got residual xanthate in your water, you recycle your water, you just need to add less xanthate in the next round. It could be a benefit to the industry.
Hi, Kirsten. I'm not very familiar with the Bushveld deposits, but they're ultramafics,
yeah,
I believe. Do you get any talc in those deposits, and how does that behave as a gang mineral with this sort of chemistry, flotation chemistry? It's a pain everywhere, but yeah, I was just wondering specifically about talc as gang.
Yes, talc is definitely present in the ores in various quantities. So some ores have far more talc than the others, but even the tiniest little amount of talc is going to influence the process. Talc floats by itself, as I'm sure most of you know, but with ions in the system, talc floats even better. But with ions in the system and a depressant, you can more easily depress talc. So there's a balance between how you treat talc, even though it's a small component. The problem with talc is that it forms these rims around your gang minerals. So even though it's 5% or 2%, it's so widely dispersed throughout your ore that it can have a much larger impact than you expect it to have. So we published a while ago about these talc rims around all your they sit around the gang. I mean, they're oxidation products of the gang, or alteration products. So they really are problematic, and we have the same problems with talc in South Africa as I'm sure you do here.
All right, well, if there's no more questions, please join me in thanking Kirsten for her presentation today.